So I'll begin this with a definition of an initial segment of a well-ordered set W given by element U, and it is just the set of all things less than U. We'll prove this lemma: no well-ordered set is isomorphic to an initial segment of itself. An initial segment necessarily cuts something out of it, namely at least U and possibly more. This makes U something like a, so to speak, strict upper bound for the initial segment, and yet the corresponding thing in the initial segment, right? There is no such element U in the initial segment, right? Because it's everything less than that, so U, or anything corresponding to U, would not be included. That makes something like a structural difference between the set W and its initial segment. Therefore, there really shouldn't intuitively be an isomorphism if we have defined the notion of isomorphism well, and we seem to have. So, okay, so that's why we should not expect there to be an isomorphism. And we also, from that description, think that looking at U itself and what the potential function would map U to, that's a good place to look for our proof. So let's call the initial segment A, suppose that F maps W to A, and ask the question, what does F map U to? Again, here, assuming that F is an isomorphism. Well, if F maps U, it must map it into A. Because it is in A, by definition of an initial segment, that element must be less than U. But F is an increasing function, and we've already seen that for all elements it satisfies this inequation. That's a contradiction. The isomorphism cannot exist. A next theorem. If W1 and W2 are well ordered, then exactly one of the following three holds. Either they're isomorphic, or an initial segment of one is isomorphic to the other. So, we begin with a few definitions just to sort of smooth the statement of the proof. The first definition is that Wi of U will denote the initial segment of Wi given by U, and I could be 1 or 2. We also define this function, F equal to the set of all pairs from W1 W cross W2, such that the initial segments are congruent. Oops, this should be a Y in there. But, so to illustrate this function F, suppose that I take W1 to be this infinite list of elements with least element 1 going out to an infinite collection of elements. But these 1, 2, 3, 4 are really just names. I don't define operations on them per se. But but they are well ordered, and 1 is the least element, and every finite subset has a least element, so on, right? W2, I have named its elements in the Hebrew alphabet, starting at Aleph, going to Bet, Gimel, Daled, and just for variety, I chose a finite list, but of course W1 could be the finite set, and W2 could be the infinite, or they could both be finite, or they could both be infinite. So, but this is just one example. In this example, if we look at the initial segment given by 1 in W1 and the initial segment given by Aleph in W2, those are both the empty set, and it is not hard to prove that the empty set is isomorphic to the empty set. It's quite trivial. The first, even somewhat interesting isomorphism is between W1 of 2 and W2 of Bet, and so on. The isomorphisms for each corresponding elements exists, and it implies that these elements are in the function F. So there you have it. In the next video, I will actually get into the proof, but this was all just kind of setting the stage for the proof.